Hello, my name is Sejong Lee, a postdoctoral researcher at King's College London. I'm going to talk about my recent research on candidalysin peptide, single molecule detection of multiple transition states of membrane-perforating peptide toxin candidalysin. This research was performed in Professor Julian Nagel's group at King's College London and funded by Wellcome Trust. Fungal infections are a global concern as it affects over 1 billion individuals worldwide and kills 1.5 million annually. In 2016, the first peptide toxin in any human fungal pathogen was discovered in Candida albicans. Candida albicans express EC1 protein. EC1 protein is digested by caxin into 8 peptide fragments. The third fragment is the toxin. It was named candidalysin, and its sequence is shown here. It has 3 lysine residues at the C-terminus. Orthologs of Candida albicans candidalysin were also identified in Candida dubliniensis and Candida tropicalis. Candidalysin directly causes cellular damage and immune activation during mucosal and systemic infections. And the secondary structure of Candida albicans candidalysin and its orthologs have alpha helices and beta-term motifs. This is a predicted structure by Pefford, and it's important to have the helicity for membrane-active peptides. However, the mechanism of cellular import remains unknown on a molecular level. Here we reconstituted planolipid bilayers in a multiple array device using ORB16 and monitored the membrane permeation properties of candidalysin using electrical recording. We monitored candidalysin-induced membrane permeation properties at positive and negative applied potentials. Both at -50 mV and +50 mV showed membrane damage. At -50 mV, where electrostatic forces are induced for the lysin-rich C-terminus region of candidalysin, unstable and varied current steps were observed. Varied current levels indicate membrane pores of various sizes. The mean conductance of membrane pores was estimated at 0.2 nanosiemens. However, at +50 mV, small noise current levels and a current jump were observed, indicating a transition from a pre-pore state to the final pore state. The mean conductance of the membrane pores was estimated at 0.88 nanosiemens. To investigate the effect of electrostatic interactions and the roles of lysine residues at the C-terminus of candidalysin, we introduced substitution mutation of lysine with alanine. We tested single lysine to alanine mutation and double lysine to double alanine and triple lysine to triple alanine mutations. First, we observed the helicity of the substituted mutants using circular dichroism. In comparison with candidalysin wild type, single lysine to alanine substituted mutants showed significantly reduced helicity. And among the single lysine to alanine mutations, A1 showed the lowest degree of helicity, indicating that both the density and distribution of lysine residue throughout the candidalysin contribute to the stability of alpha helical structure of candidalysin. More than 2 lysine substitutions showed completely unordered structures. Furthermore, we monitored the membrane permeation properties of these mutants. Latencies until the membrane permeation by each mutant are plotted. Substitutions of alanine for lysine increase the latency for membrane permeabilization by a factor of 6 up to maximum 30, showing that lysine side chains have an influence on the membrane permeabilization activity. Greater influence with double, triple substitutions compared to single substitution, indicating that charge-dependent electrostatic force play a role in membrane permeation by candidalysin. In addition, we monitor the cellular damage by candidalysin and its mutants. Oral epithelial cells were treated with candidalysin and its lysine-substituted mutants. And 24 hours later, the amount of released lactate dehydrogenase was quantified. The LDH is an indicator for cell damage, and all lysine-substituted mutants, but A2, A3, showed a significantly reduced cytotoxicity. Our results demonstrate that lysine side chains at the C-terminus of candidalysin play a crucial role in membrane permeation activity and cell damage activity. In summary, our work provides valuable insights into the dynamics of candidalysin import, which can be used to design therapeutic agents for the fight against fungal infections. Thank you for watching this video, and please feel free to contact me if you have any further questions.